Hello students, very good afternoon. My name is Ravi Ranjan Kumar and I welcome you to this session. This week we are revising mechanical properties of matter. We have already covered viscosity and now we are going to start surface tension. This will take 2 classes. Okay, so in today's class I'm going to introduce the concept of surface tension. Okay, like how it is defined as surface tension force per unit length or surface energy per unit area. Okay, and then we will look into some problems. And in the next class, we will take the concept of capillary rise and contact angle, etc. Okay, so without losing any further time, let us share our screen here. Okay. So here we go. So as we all know that surface tension is a property of liquid or static liquid, you must say, by the virtue of which its open surface behaves like a stretched membrane. It remains under the state of tension. Okay, so when we say that it remains under the state of tension, what do we mean here? Let's say, for example, there is a container, okay, and say some liquid is filled inside it. So its open surface, okay, will be like this. And if we imagine, or if we draw an imaginary line on the surface, okay, so this line is going to divide the surface into two parts, let's say part 1 and part 2. So when we say surface tension, this surface is under state of tension. What do we mean is, like, for example, the part 1 is going to exert some force on part 2 along the surface. Let's say, for example, this would be like F21. Okay, that is force on part 2 exerted by part 1, and equal and opposite force would be exerted by part 1 on 2. So like that would be F21. So clearly we can see that F21 is nothing but minus F12 over here. Okay, and we must realize that the magnitude of these two forces are nothing but equal, and let's say this is F, and this force here is basically known as surface tension force. Okay, so that is nothing but the force exerted by the one side of the liquid molecules on the surface on the another side of liquid molecule on the surface, okay, which are in contact with an imaginary line drawn, okay, on the surface. Okay, so that clearly basically is the surface tension force is nothing but clearly the force of interaction between the molecules on the surface, okay, which lie on this line over here. Okay, so when we will be talking about the magnitude of the surface tension force, okay, it is obvious that it is going to be directly proportional to its length. Okay, so the proportionality constant that we will be having over here, let's term it as sigma. So F is equal to sigma L, or rearranging this equation, sigma, we will be getting it as F by L. And this sigma, this proportionality constant, you must realize is a property of liquid, and this is known as surface tension of given liquid. Okay, so one thing is clear, like for example, if we draw an imaginary line on the surface, okay, like liquid molecules from the one side of this that line will be exerting some tangential force on the liquid molecules on the other side of that line, and that force is going to proportional to that length, and this sigma here is proportionality constant, which is surface tension of liquid. So since now we are talking about a new force, which is surface tension force, and we have already written its magnitude, and now it's time to look into the direction also. Okay, so what would be the direction of surface tension force? Let's look closely. Direction of surface tension force. So clearly you can see that uh, surface tension force acts perpendicular to imaginary line drawn on the surface and tangential to surface. Okay, so being said that, like for example, uh, this is the surface, and if we have drawn something line like this, okay, so the surface tension force here would be along the surface but perpendicular to this imaginary line. So whatever is the length of this line, okay, let's at any position the length is dl. Okay, so this df is gonna be equal to sigma times dl, and let's say this is a open surface. Okay, so that we understand that it is going to act perpendicular to whatever imaginary line we are drawing, and it will be tangential to the surface as well. So that being said, okay, we have looked into the direction of surface tension force, and when we are saying that sigma is equal or F is equal to sigma into L, so sigma is a mechanical property of fluid, and let's look more into this physical quantity. Okay, so let's talk about surface tension of liquid. Okay, so looking at this expression, we clearly realize that the sigma is equal to F by L. So its dimension, we can clearly write that would be M L to the power 0 and T to the power minus 2 simply. Okay, so its SI unit, you must realize, SI unit is going to be Newton per meter, and CGS unit, you can write unit of force is dyne. Okay, and unit of length is centimeter. So this is one information about surface tension of liquid. And the another thing, like when the temperature of the liquid changes, obviously the surface tension of liquid will also change. So let's look at that dependency. So you must realize that surface tension of liquid decreases with a rise in temperature. Okay, and surface tension of liquid is related by this relationship, that is according to Ferguson. Okay, sigma is equal to sigma naught into 1 minus theta divided by theta c to the power n. So let's try to look into each and every term. So sigma obviously is surface tension, and you must realize that sigma naught here is nothing but the surface tension of liquid at 0 degrees Celsius, and this theta is nothing but absolute temperature. Theta should not be taken in degrees Celsius. Theta is absolute temperature, and theta c is nothing but the critical temperature of that liquid. Critical temperature means like where the interface between liquid and its vapor phases will disappear. I hope you understand the meaning of critical temperature. And another, like this n, the exponent n is a constant. N is a constant, and it will depend on the liquid itself, like what liquid we are taking. Okay, so that clearly you can see, first of all, that sigma decreases with increase in theta, you must clearly understand. And another thing I want you to notice, that at theta is equal to theta c, like the sigma will become equal to 0. Like at critical temperature, the surface tension of the liquid vanishes. There will be no surface tension of the liquid, because see, at that temperature there would be no difference between liquid and vapor phases, and obviously vapor, which is gas, will not exhibit any phenomena of surface tension. So these were some facts about surface tension of liquid. One more thing we must know is the effect on the surface tension of liquid when some impurities is added into it. Okay, it's like when impurities will be added, the surface tension of liquid will change appreciably. So you must realize that it increases, okay, when a highly soluble material, like for example NaCl or ZnSO4, if these type of materials are added, okay, it increases when highly soluble material are added. Okay, the reason being, like for example, these are having ionic bonds, so when they will be added, the interaction between the liquid molecules will increase. So obviously the interaction between liquid molecules in the surface will also increase, so they will be exerting greater force on each other. That means greater surface tension. Okay, so, and another thing is, like oppositely, it decreases when a sparingly soluble material, or salt you can say material, for example, you can take phenol, or or you can say detergent. That is one of the thing you must know, that when detergent is added into water, its surface tension decreases, okay, which helps us, okay, in cleaning of clothes, etc. Okay, so when any sparingly soluble material is added into the liquid, okay, so the interaction between the molecules on the surface decreases, so surface tension also decreases. So these were some facts about surface tension you must know. Okay, so we have already talked about surface tension, the definition of surface tension as surface tension force per unit length. Okay, so there is another way of defining surface tension in form of surface energy. So let's talk about that. Surface energy. Okay, so imagine a container in which some liquid is present. Okay, so we will be dividing the molecules of liquid into two categories, one which is inside the volume and the another which is on the surface. And you must realize the molecule of liquid which is inside the volume will be surrounded by other liquid molecules from all sides. Okay, so its energy, if we want to write down, like here the potential energy of this molecules, if we want to write down U, okay, and the interaction energy between each pair of molecules will definitely be negative, because the forces here are attractive in nature, and let's say it is surrounded by n molecules on interaction energy of one pair is E, so that would be minus n times E. That would be the potential energy of any molecule inside the volume. Okay, and now let's imagine the molecule which is on the surface. So it would be surrounded by liquid molecules from only one side, bottom side. Above it there are only air molecules. So when we will be looking at its potential energy, okay, let's say this is ui and this is u surface, you can say. Okay, so only half the number of molecules will be interacting with this molecules on the surface. So u on the surface, you can simply write that would be minus n by 2 times E. So you can clearly see that US, the potential energy of the liquid molecule on the surface, interaction potential energy, I'm here not talking about any gravitational potential energy. So US would be greater than UI, that you can clearly realize. This is, you can see, less negative and this is more negative. So US is greater than UI, you must realize. So what we can say, that the molecule on the surface of the liquid are more energetic than the liquid molecules inside the volume. Okay, that means if we want to bring any molecule from inside the volume onto the surface, we need to do some additional work. Okay, and that work done would be stored in form of a potential energy. So W external, you can say, in order to bring any molecule from the volume to the surface, is going to be nothing but US minus UI. Okay, and that will be stored like that. You can say that would be delta U. So that will be stored, that difference will be stored in form of potential energy or change in potential energy for the surface molecules. So this is the idea. Okay, so this is something called surface energy. This term is nothing but uh, change in surface energy, you can say, or simply surface energy, you can say. So how do we measure the surface energy? Okay, so in order to measure the surface energy, we can conduct one experiment. So let's say this is a thin wire frame. Okay, and let's say there is a slider of negligible mass which can slide over this thin wire frame, and here we have a liquid membrane of surface tension sigma. Okay, and let's say we are exerting some external force F external over here to move that thin wire frame slowly in this direction. Let's say we want to displace it by dx. Okay, so what would be the magnitude of this external force we need to apply in order to slide it slowly? Okay, so that means, like, if we can take a this system, means this wire plus some molecules, okay, which are in contact with each other. So now you must realize, let me use other color pen. So due to surface tension, okay, this imaginary line, let's say its length is L, will be experiencing a force sigma times L. And also you must realize this is a thin membrane. So there are two open surfaces, okay, one at the top and one at the bottom. You should imagine any membrane has two open surfaces, one at front and another at back. So this is sigma times L from one side, upper side, and sigma times L from the lower side. So net surface tension force is going to be 2 sigma times L over here. So the magnitude of this external force which we required in order to move that slowly is going to be 2 sigma times L. Okay, so what would be the work done by this external force? So we must simply write like dW external is going to be equal to nothing but 2 sigma L into dx. Now you realize, and using a work energy theorem, dw external is equal to du plus dk, you can write. And since we are moving it slowly, okay, so this dk term will be equal to 0. So we will be left up with du is equal to 2 sigma L dx. And now you notice L dx is the increase in surface area at one side. So 2 times L dx would be increase in total surface area, like for example both sides. So this can be rearranged to write du is equal to sigma times dA. So change in surface energy is equal to sigma times change in area. So that is a very, very important definition. And this gives an alternate way of defining the surface tension of the liquid, or having an expression in terms of energy for surface tension. This is simply du by dA. So what you can say, surface tension can be also measured as surface energy per unit area, or you can say surface energy, change in surface energy per unit change in surface area. Okay, so whatever you want to say. So this is an alternate way of defining surface tension of a liquid, or measuring surface tension of liquid. So now, since we have defined the surface tension already, and we have looked into the surface tension force and the surface energy, okay, so let's now try to solve some problems. Okay, first we will be focusing on the force part. Okay, we will be doing all the problems by analyzing the force, and then we will move into the energy analysis also. So one simple question I'm going to take here is, let's say we have a thin liquid membrane. Okay, and this liquid is having surface tension as sigma, and over that liquid membrane, let's say a thin thread is put over here of length L, which is closed. Okay, so this is having some random shape. So what now we are doing? Okay, let's say we pinch a hole in the inner part of this membrane. So what will happen? Let me tell you. Okay, so this here will get stretched. Okay, this thread, which was initially having some random shape over this liquid membrane, when if we pinch it here, okay, so this liquid membrane will burst, and this thread will take a circular shape, and there will be some tension, okay, inside this thread. Okay, like the thing would be, there would be liquid membrane all around it, only we have pinched it inside. So this here, due to surface tension, will be under the state of tension. Okay, this thread will be under the state of tension, and we wish to find out the surface tension force or tension in this thread over here. So let's say this would be the center of this circle. Okay, and let's take a small angle d theta, and let's take this part of the thread and let's draw the free body. Let's draw the free body diagram of this, or analyze the force acting on this part of the thread. So you must realize, like, this part of the thread is in contact with the remaining part of the thread also. So here it will experience a tension which is inside the thread in tangential direction, and here it will be same tension due to symmetry, you can say, that would be tangential to this circle. And apart from that, there would be surface tension force, you must realize, that would be along the surface and perpendicular to that line. Okay, so we are gonna balance all those forces. The magnitude of this surface tension force is going to be sigma times this length over here, which is nothing but r d theta. And you must understand, this is a liquid membrane, so this has two open surfaces. So sigma r d theta is the force from only one side. So 2 times sigma r d theta would be the net surface tension force, which would be acting on this small element of the thread over here. So if we balance, so this T and this T will be having a component, net component towards the center, and when we will be balancing these forces, so simply you will be getting 2T sine d theta by 2, and that you can say that will be equal to 2 sigma into r d theta, right? So this 2 and this 2 you can really cancel, and also, like, this d theta is very very small, so sine d theta by 2 would be approximately equal to d theta by 2, so that would be equal to sigma into r into d theta over here. So you can also cancel d theta as well. So t, what we are getting is nothing but 2 sigma times r. And r, how we can find out? So see, the length of this thread is nothing but L, which would be the length of circumference over here. So L, you realize, is nothing but 2 pi r. Okay, so r is nothing but L by 2 pi over here. So that would be simply sigma L by pi would be your answer. Okay, so that's one of the question. Let's take a few more questions, okay, which would be based on force. So here, so let's say we have a thin liquid membrane, okay, whose two sides, let's say, are fixed. This is like a thin membrane, okay, and let's say the length here of this is 2a, okay, and you can imagine this to be a thin film of liquid which is maintained between two very long thin parallel horizontal wires. So these are, let's say, two thin horizontal wires, and they are separated by a distance 2a. So what now we are intending to do, like, we are intending to put a wire over here, a long wire of mass per unit length lambda, and which is gently placed over the liquid film at the middle of at the middle parallel to the wires, you can say. This is how we have put. So the thing that would be happening finally, if we place it gently, so what would be happening over here is something like this. So this membrane, thin membrane, that is very, very thin, you must understand. Okay, so this would be the shape due to the weight of this um, in a wire over here. Like there would be some depression in this, and let's say this depression has been measured to be equal to y. Okay, this depression has been measured to be equal to y, and now we want to find out the surface tension of the liquid. We want to find out the surface tension of the liquid, and mass per unit length is given to us, and how much depression it would be, that has been given to us. So how are we going to approach this problem? So what we are going to do is simply we are going to draw the free body diagram of this part. Okay, for unit length, let's say, or for length L, you can say it would be experiencing a vertically downward force, which would be its weight, and that would be nothing but lambda L times G. And you must realize there would be surface tension force here, surface tension force here. Now, like, it is clearly visible to you now in this, at least in this diagram, that it has two interfaces. So along those two open surfaces over here, the surface tension force would be acting. So length is L, so each of these would be sigma L. So net force here you can write 2 sigma L in this direction, and 2 sigma L in this direction total. Okay, so that is the idea. Okay, so these forces are acting on this enclosed part of the system. Okay, and now we must assume the force balance now. So let's look at the geometry a little bit. Let's imagine this triangle. Let's say this angle here is theta, and this is y, and this base here would be nothing but a. So when you will be looking at the force balance, you can see the horizontal component of surface tension forces will be cancelling each other, and the vertical component of surface tension force will be balanced by lambda Lg. So what you can basically write, so that would be 2 sigma L sine theta would be the component of this along vertically upward direction, so into 2, because we have another component of this surface tension force also, and that will be balanced by its weight, which is nothing but lambda times L times G over here. So now we must realize that is nothing but L will get cancelled over here, so that would be 4 sigma. And now in order to find out the sine theta term, we have to take a little bit of approximation. Now see, like this y is very, very small. So if y is very, very small, theta would be very, very small as well. So sine theta and tan theta would be approximately equal, and sine theta is approximately equal to tan theta, and tan theta here you can see is nothing but y upon a. Okay, so this will give us sigma is equal to simply lambda ga divided by 4y. So that is how in this question we were able to measure the surface tension of the liquid. Now let's take one another example very, very quickly. Okay, and that example like once appeared in like IIT JEE 2003. Okay, so that is very, very interesting problem. So let's say we have a pipe. Okay, and this pipe has a tube. Simply this tube has radius b, and some air is blown. The air's density is rho, and it is blown with some velocity v in this tube. Okay, and here we are having a thin liquid membrane. Okay, and due to this blow, okay, the size of membrane, like a bubble will be formed over here, you must realize, and the size of bubble will keep on growing, and at some stage, let's say when the radius of this becomes r, okay, it will detach from this boundary. Okay, and we wish to find out over here, the question is, when we are blowing this air with velocity v over here, the surface tension of the liquid that is given to us, let's say that is sigma. After some time, the bubble having grown to radius r, you can say, or small r, let's take, grown to some small r, okay, separates from the tube, and we have to find out that value of r, imagining this r is much greater than b. So this r is much greater than b. Surface tension is given to us, so we want to find out that what would be the radius at which it separates. So just we need to do the force balance. Okay, and we have to also assume that when this air is coming and the striking the surface, it is immediately coming to rest. Okay, so what we can understand, like you also have understood the thrust force, or you can also use the concept of force is equal to rate of change of linear momentum. So when this air is moving inside it, okay, the dp by dt, the force exerted by this would be like dp by dt. You must realize this would be the force exerted by the air, and that would be nothing but, you can say, v times dm by dt, and dm by dt you understand is nothing but rho a v. So this basically is nothing but rho a times v square, where a is nothing but this area, the area of this tube over here, which you can see is nothing but pi b square. So that is rho into pi b square into v square here. So that is the force that has been exerted by this flow of air on this bubble. That is why the size of this bubble is growing. And apart from that, you must realize on this bubble, okay, like a thin layer you consider, so there would be a surface tension force which would be along the surface and perpendicular to this periphery, you can imagine. Okay, so that would be like forming a conical shape. Okay, so the radially outward component or radially inward component of these forces will cancel each other, and the axial component will get added up. Okay, so the axial component we wish to find out, axial component of surface tension force, let's say F axial surface tension force, would be nothing but the net magnitude of surface tension force is going to be sigma times length is basically 2 pi b of this periphery, and that multiplied with 2, because we have a thin membrane so which has two open surfaces. Okay, and let's look at some geometry here as well. Let's say, for example, this is the center. Okay, and let's look at this. So this radius is r, and this radius is b, and this angle is theta. So you can clearly, in this right angle triangle, you can see that sine theta is nothing but b by r. So here basically the axial component would be the sine component here. So this would be the force. So obviously these two forces, like the force exerted by the air and the surface tension force which is acting along the axis of this tube in leftward direction, they will be balancing each other. So the balance here you see, that is rho into pi b square into v square will be equal to, like you can say, 4 pi sigma into b, and sine theta obviously is nothing but b by r. So this, first of all, this b gets cancelled and this pi also gets cancelled. So what we are getting it over here is r is nothing but 4 sigma upon rho v square. So this would be the radius of this bubble at which it will get detached. So I hope you understand this problem. Now let's take one more problem which will demonstrate the idea of surface tension even more. Okay, so let's say what we have is a thin wire frame. Okay, and a film of soap solution is created inside a loop formed by a rectangular wire frame, as you can see, and an extensible light thread AB. Okay, so there is a thread AB over here, and here we are having a liquid membrane. Okay, and this is forming some semicircular shape. Okay, I hope you realize. Okay, and its length here is L. And what we are now doing is, by pulling the midpoint here, pulling the midpoint of the thread with a force F, the thread can be given another shape, let's say this kind of shape. So we have two semicircles, okay, and this force we need to do this is, let's say, F. Previously this was single one semicircle, so basically you must realize that this angle here is 90 degrees. So here now we are having two semicircles, and in this arrangement the magnitude of this force F is known to us. Okay, and here the thread has been given shape of two semicircles. Okay, and we are required to find out the surface tension of liquid in this case. So now looking into this case, okay, so what we can say, like, let's draw the diagram again. So we have two semicircles. Okay, so only this part if we consider, and if we look at the symmetry of this thing, we can clearly see, like, looking at the symmetry, total force is F by 2. So F by 2 and F by 2 would be, let's say, tension at this point in each of these threads. If we divide it basically in two parts, and due to symmetry, we can say also, like, this would be F by 2 and this would be F by 2 as well. So total force, okay, exerted by this contact and this contact, and the pulling force F over here, the total force that this thin membrane or this thread is experiencing in vertically upward direction is the sum of all these quantities, that is nothing but 2F. And now let's imagine this section of membrane, okay, and let's take the equilibrium of this section. Okay, so obviously it is experiencing 2F force in vertically upward direction, and it would be experiencing some surface tension force in downward direction, you must realize. So what would be the magnitude of this force over here? So let's for instance, this radius, let's take, that is R. So this total length would be 4R. Okay, so sigma into 4R would be the force from one side, and since this is membrane, so this has two surface, so this would be net surface tension force. Okay, and this thing is in equilibrium, so what we can write is 2F is equal to 2 sigma into 4R we can write, and rearranging we are getting sigma is equal to nothing but F divided by 4R. And now you must realize, like, here, like, total length of this thing was nothing but L, and this length is pi r, this length is pi r. So you must realize that 2 pi r is equal to L over here. So in place of r, since the given quantity in this question, that is L, we can substitute L, and what we will be getting here is, that would be F by 4, and r we are substituting with L by 2 pi. So this we are getting it as pi F by 2L over here. So that would be the surface tension in this case. Let's take one example quickly, one another example quickly, which is quite an interesting example. Okay, so the forming of meniscus problem. So let's say this is some surface of aquarium, okay, and some liquid is filled inside it. So near the surface, you must know that it forms some meniscus. Okay, this is the meniscus, and let's say the height of meniscus we are required to find out. What would be the height of meniscus? And the things which are given to us is the density of this liquid, okay, and the surface tension of this liquid is given to us. Okay, so what would be the height of meniscus formed over here? So in order to do that, like, what we are going to do is we are going to consider the equilibrium of this part of the liquid. We are going to consider the equilibrium of this part of the liquid. And let's, for instance, imagine the width of this wall of this uh, uh, aquarium. Okay, so let's say that is L. Okay, L inside, you must realize that is L inside, which is not visible in this diagram. So we are looking for the equilibrium of this part. Okay, so now you see what all forces are acting on that, and we are looking for the horizontal equilibrium. So you must realize, okay, like the atmosphere would be pressing it from this side. So effectively, this force we can find out. So the projected area would be nothing but if this is H, the projected area would be L into H, and the atmospheric pressure is, let's say, that is P naught. So atmosphere will be pressing this meniscus, okay, with this much horizontal force. Please understand, we are only writing the horizontal component of force, okay, because we are doing horizontal force balance. Okay, so this is its expression. And apart from that, since liquid is also exerting some pressure on the wall of this aquarium, equal and opposite force will be applied by the aquarium on the liquid as well. Okay, so what would that force be? So in order to do that, like for example, you should realize at this level, the pressure inside the liquid will be P naught, because that is at the level of open surface. So this is at greater height. So let's say this is H. So the pressure here is going to be P naught minus rho GH. Okay, so the force which will be acting from this side would be the average pressure times area. So the average pressure, you must realize, would be P naught minus rho GH by 2, the average of this quantity over here, and that multiplied with area, that would be nothing but L into H over here. So this is the force acting on this element of liquid from left side. Okay, and apart from that, now you must also realize, okay, over here there would be a length of line of L length. So okay, so surface tension force will be acting along the surface, and that would be equal to simply sigma times L. So these three forces, first of all, from this direction, this force and this force and this force are acting. Okay, so you can see like this minus this will be basically this term will get cancelled. So effectively we will be having this term only in leftward direction, and that will be balanced by this force in rightward direction. So the force balance equation will be sigma L is equal to rho g h square by 2 into L over here. So obviously this L which we assumed in the very beginning is going to cancel out over here. So H we are getting by rearranging. So that is nothing but 2 sigma by rho g under root. So that is a problem you must understand. So these were some questions we discussed with the help of concept of surface tension force, and in these problems we took the force balance in order to get the unknowns. Okay, so now let's try to look into one more concept, and that is something called excess pressure inside a surface having two curvatures. Okay, let's say whenever we are defining the curvature of a surface, okay, generally we can define it by defining two surface curvature or two radii of curvature also. um, so I will be explaining it more, okay, by giving some examples, but let's get an expression for the excess pressure. So let's write the heading excess pressure inside a surface having two curvatures. Okay, so let me brief that in very beginning also. Let you might have seen like a tire tube. A tire tube, you all might have seen something like this, or you can say donut also. So if you look at this point over here, so first curvature is this. Okay, so that would be part of some circle. you must understand. And there you can define at this point another mutually perpendicular curvature, that would be this. Okay, so two curvatures over here, like the center of curvature of one would be this. Let's say this would be r1, and the another curvature would be this, and this its center of curvature would be somewhere here, and its radius of curvature would be something else. So I hope you are understanding what I mean when I am saying the two curvatures of a surface. Okay, so let's say we have a very small, we have taken a very small element of surface area, say something like this. Okay, and this is one curvature I am showing, and this is the another curvature I am showing. Okay, and the radius of curvature of this part, this small part, is, let's say, r1, and here is the center of curvature of this part. So basically this is r1, and let's say this angle here is d theta 1, and let's look at the another curvature. So this is c2, and this here is nothing but, let's say, d theta 2 over here. So all around you must understand, I have only uh, disclosed two sides, but two other sides would be at the back also. Okay, so now you must realize, let's say this is the open surface of a liquid, or this is the interface between two different medias over here. So at the surface of liquid there would be surface tension force, which would be acting perpendicular to this surface, but perpendicular to this line, but along this surface these forces would be acting. Okay, and the magnitude of this force is going to be equal to, the magnitude of this force is going to be equal to proportional to this length. So this force, you can say simply, that would be sigma, and this length is nothing but r1 times d theta 1, and this force here would be nothing but sigma into, and its length is r2 d theta 2. Okay, so these are the forces. And let's take another view of this thing. Like if we have a front view, this is how let's say this curvature of radius r1 will look like. So this is r1 and this is d theta 1. Okay, so a surface tension force will be acting, this force would be from this side, so that is sigma r2 d theta 2, and this is nothing but sigma r2 d theta 2. Okay, and this will be having, you must understand, like the horizontal component of these two forces will cancel each other. Okay, and the vertical component will add up. Okay, so basically this surface tension force is trying to exert a force in towards the center over here, towards their respective centers, okay, on this small area. So in order to balance that, there must be some pressure difference. So let's say this pressure is p1 and this pressure is p2. So the pressure difference, let's say delta p, is p1 minus p2. So basically a force would be acting in this direction, which would be balancing this surface tension force. So this force is going to be delta p times the area of this surface. Okay, so we will be again be looking at the force balance. So what would be the total force towards the center over here? So these two forces, and apart from that, if you look it from left or right side, okay, you will be looking at sigma r1 d theta 1 on one side and another sigma r2 r1 d theta 1 another side. So basically these two forces here, let's take their central component over here. So basically this angle is d theta 1 by 2. So this angle here would be d theta 1 by 2 over here. So basically we are looking at the sine component. So net force inside, that would be nothing but 2 sigma r2 theta 2, or d theta 2, you write sigma r2 d theta 2, and its sine component, so that would be sine d theta 2, or d theta 1 here, it would be, this is d theta 1, so d theta 1 by 2. So this would be the force. Okay, and 2 times, basically 2 components we are taking. And similarly, one more component we will be having, that would be 2 sigma r1 d theta 1 into sine d theta 2 by 2. This time we will be writing, and this will be equal to nothing but this delta p into area. And what would be the area of this? So this would be like a rectangle, and one of the side is nothing but r1 d theta 1, and the another side is nothing but r2 d theta 2. And theta 1 d theta 1 and d theta 2 are small. So what basically we can do in this relationship, 2 sigma, let's take common, okay. And so basically this d theta 1 by 2 is approximately equal to d theta 1 by 2 only over here. So we can also take d theta 1 and d theta 2 common, and this 2 will also get cancelled, okay. And we will be getting in the bracket, okay, we will be getting nothing but r1 plus r2, okay. And the right hand side here would be nothing but delta p into r1 r2 into d theta 1 into d theta 2. So this term here will get cancelled. So what basically we have got is delta p is equal to sigma into 1 by r1 plus 1 by r2 over here. And this relationship we have just got by considering the force balance of this thing. Okay, so where r1 is the one of the radius of the curvature and r2 is the another radius of the curvature of the curved surface. Let's say, for example, let's take some examples over here. So one example I am going to take is for the cylindrical surface. Excess pressure inside a cylindrical surface. So say we have a cylindrical surface, okay, which separates this liquid and some another media over here, another, let's say, gaseous media, okay, which separates, okay. So now here, okay, so how will we define the two radii of curvature of this surface over here? So first of all, the radii of curvature would be one radii of curvature would be r1, and the another curvature is basically flat. So basically uh, r1 would be basically the radius of curvature, or simply the radius of this cylinder, and r2, which is for corresponding to the flat surface, r2 will be tending to infinity. So in that case, the excess pressure, okay, and you must understand the pressure would be greater at the concave side and less at the convex side. So if we are writing this is p inside and this is p outside, so obviously p inside is greater than p outside, and this delta p would be nothing but sigma into 1 by r1, which is r, and 1 by r2, which is infinity. So this term will be approximately equal to 0. So excess pressure would be simply sigma by r. So if we have, for example, if we have a liquid drop, okay, which is spherical in shape, so excess pressure inside a liquid drop, and which is basically spherical in shape, what we can say that r1 will also be equal to r and r2 will also be equal to r. Like say, for example, at this point, this is one of the curvature and this is another curvature. So the radius of curvature of both mutually perpendicular curves are basically equal to r. So in that case, delta p will simply turn out to be 2 sigma by r over here. So that is excess pressure inside a liquid drop. And another thing we must notice here is something, excess pressure inside a liquid bubble. Okay, so the difference between a liquid drop and liquid bubble you must realize, whereas the liquid drop will only have one interface, a liquid bubble will be having two interfaces. Let's say, for example, outside is air and inside is air. So there is a thin liquid membrane, okay, of, like, this part is made up of liquid and this is very thin. So for example, if this is R1 and this is R2, or let's say inner radius and outer radius, so you can say that R1 is approximately equal to R2, and let's say that is equal to R over here. So now you see, let's say this is P1 and this is P2 and this is P3 over here. So first of all, you should realize that P1 minus P2 would be nothing but 2 sigma by R1, which is nearly R. And you must also realize that P2 minus P3 will also be 2 sigma by R2 this time, which is also approximately equal to 2 sigma by R. So when you will be adding these two equations, basically P1 minus P3, or the inside pressure minus outside pressure, or excess pressure inside a liquid bubble, you will be getting that is 4 sigma by R. So that is the excess pressure inside a liquid bubble. Please understand the difference between these two relationships. This is the excess pressure inside a liquid bubble, and the previous result was the excess pressure inside a liquid drop. Okay, so that being said, let's take one simple question here. Imagine uh, two large discs, okay, two very large discs over here, or plates, can imagine. Okay, and a thin layer of liquid, sorry, is between these two plates. Okay, so when you try to pull them apart, a curved surface of the liquid, some liquid will be between them. Okay, so what happens if you want to pull it? Okay, you need to apply some external force in order to separate these two discs. Okay, and I wish to find out the magnitude of this external force over here. So what is the force? And the parameters that are given in this question is, let's say at this instant the separation between this plate is D over here. This is the separation between these plates, and this angle, basically this is known as angle of contact, about which we will be discussing more. This is given to us as theta over here. Okay, and it is also given like this D is very small. This D is very small in comparison to the radius of this disc over here. Okay, so in order to find out, okay, the force which we need, let's first try to understand the physics of it. So let's understand, like, the atmospheric pressure outside is, let's say, P naught. So here there would be like, say this is the concave side and this is the convex side. So the pressure inside this liquid over here would be less than the atmospheric pressure, that is P naught minus delta P. So the pressure inside the liquid here is smaller than the pressure outside. The pressure outside is P naught and P naught. So basically from both the sides, the atmosphere will be pushing it, pushing those disks towards each other. So in order to separate, we need to apply equal and opposite force, and that force would be nothing but the pressure difference. The pressure difference is definitely going to be delta P times the area of this plate over here, that is the area of this disk over here. And so that would be the external force. So F external is nothing but delta P into the area of the disk. Let's say area of the disk is given. Let's say this is some capital R. So A is delta P would be equal to into pi r square. And we now want to find out this delta P to substitute it in this equation. So what would be delta P? Now you see, this is again a curved surface. So there would be two radii of curvature. One would be defined by this circle, and another would be defined by this circle over here. Another would be defined by this circle. So now you understand the center of curvature of one part is here, let's say C1, and let me use another color pen. The center of curvature of another part is C2 over here. Okay, so delta P, when I will be writing, that is, for example, imagining the pressure is at excess here. Okay, so delta P would be nothing but, let's say this is some small r. So according to our formula, that would be 1 by sigma into, let's say, 1 by r plus 1 by r. And this capital R is much greater than like this is small r. So this quantity we can neglect. So this is going to be simply sigma by r. In fact, here it would be minus sign because the curvatures are in opposite direction. Center of curvatures are in opposite direction, but it does not matter because this term has become 0 over here. So this is basically sigma by r. Okay, so when we will be substituting sigma by r, we have already got, so F external, we will be getting it as delta P into pi r square, uh, and that would be, here you can see that excess pressure is sigma by r over here. So that would be our equation. And r we need to write now in terms of this d and this theta over here. So what we can do, so this would be theta as well. So now you should realize, if I draw a right angle triangle here, okay, so this side is basically small r and this angle would be theta, and this side here would be d by 2. So clearly you can see that the cos theta, or d by 2, is basically r cos theta, you can say. So r is nothing but d by 2 cos theta. So that would be basically pi r square into sigma, and small r's value would be nothing but d divided by 2 cos theta. So that would be the magnitude of external force that we need to apply in order to find out, in order to separate these two discs slowly. Okay, so this is it for today. Okay, and we have also ended the time here. Okay, so we will continue the discussion in the next class. Thank you.